Hey, this is Mrs. Brookshire, and we are going to be talking about what is a sampling distribution. This is section 7.1. The last video that we did was the introduction to 7.1, where we reviewed some vocabulary and some symbols used in population versus symbols used in sampling. So this is actually your homework for 7.1 that's listed here. And we are going to start off by talking about, the idea of a sampling distribution. So the first definition we have is sampling variability. Sampling variability refers to the fact that different random samples of the same size from the same population produce different values for a statistic. So if you think about it, if you did a lot of random samples of the same size from the same population, those samples are all going to be different, okay? And that's called sampling variability. One activity my class did to start this chapter was we took a sample. There is a particular proportion of orange Reese's Pieces, and we went through and we did sampling to verify that or to see if we found that to be true. So think about our introductory sampling activity for this chapter. We took samples of Reese's Pieces, 30 pieces at a time, and definitely saw sampling variability in the number of orange pieces. Knowing how statistics vary from sample to sample is essential when making an inference about a population. Understanding sampling variability reminds us that the value of a statistic is unlikely to be exactly equal to the value of the parameter it's trying to estimate. So in one of my classes has 11. So we took 11 random samples of 30 pieces of candy. However, there are many, many possible random samples of size 30 in that big bag of Reese's Pieces that I had. Were we able to take all possible samples? No. But if the student took every one of those possible samples, calculated the value of p hat, that's a typo there, because we were finding the proportion of orange pieces of candy, not the mean. So if we calculated the value of p hat for each, and we graphed all of those p hat values, then we would have something called a sampling distribution, which is the main focus of, this section. And so here's the definition of a sampling distribution. The sampling distribution of a statistic is the distribution of values taken by the statistic in all possible samples of the same size from the same population. So if you could take all possible samples and recorded whatever the parameter you were looking for, which most of the time it's either you're looking for at the sample mean or sample proportion. But if you could find all of the, like in this example, all the p hats for every single type of sample, you would have the sampling distribution. Okay? So here's an example we're going to go over first. And this one, what's happening here is the problem is that John and Carol have 4 grown sons. Their height in inches are 71, 75, 72, and 68. List all 6 possible samples of size 2. Now, the population here is 4, so it's going to be really, really easy for us to list all possible samples of size 2. So the part A, that's what we're going to do. So if you start up here, I started with 71, so I did like 71, so here's part A. 71 and 75, and then I'm just listing the possible samples. That's what part A asks us to do. So we have 71 and 75, 71, 72, 71, 68. Then I went to the second one and I did 75, 72, 75, 68, and 72, 68. So there's our possible samples, okay? Part B says calculate the mean of each sample. So we're going to find the mean of each set or each sample. And then they want us to display it on a dot plot. Okay? So what I did is I just went right here beside it and I'm going to find the sample mean. So the sample mean of the first one would be 73. The next one, if I find the mean of those, it's 71.5. The next one has a mean of 69.5. The next sample has a mean of 73.5. The next one has a mean of 71.5. And the last one has a mean of 70. So then they also ask us to calculate the mean, to display it on a dot plot. So let's look at the dot plot that I've come up with down here. So I just made my dot plot. My values were 69 to 74 because I wanted to make sure I covered all of the means. And when you plotted them, we had 73, 71.5, 69.5, 73.5, 71.5 again, and then 70. And this is X bar, or the sample mean height of the brothers. So those were, that's my dot plot for that. One thing I went over here and I did is I actually calculated the mean, the population mean, which is easy to do because there's only 4 values. So I went here and I added up the heights of the brothers divided by 4, and I got 71.5. And when I look at this display here from my sample means, that's pretty good. That's right on the money because these are both 71.5. And like when you look at these, the values away, they're exactly, these two are the same as this. So it's actually going to give me an average of 71.5. Okay. All right. Part C asks us to calculate the range of each sample and then display that on a dot plot as well. So when I went through and I found the range of this first sample, it was 4. So I just kind of added it here at the end. The range of this was 1. That was 3, 3, 7. And the range of that data, of that sample, was 4. And then I went and I displayed that on a dot plot. So I made my dot plot go from 0 to 8 to cover everything. And this gave us a dot plot for the sample range of height. So the first one was 4, and then we had a 1, and then we had a 3, and another 3, and then we had a 7, and then we had a 4. Okay? So this was real easy to come up with every possible sample. I mean, a lot of times if you have a lot of values, you're not going to be able to do that. So I think another thing I did here was kind of interesting. I actually went and found the population range. And the way you would get that is take your highest brother was 75 inches and the shortest was 68, so the difference was 7. This was not very representative of the true range, population range. This one was exactly representative, and there's a word for that. Okay, we're going to talk about that in just a few minutes. So I've gotten a lot of these notes and things written out in the examples, so anytime you need to, just kind of stop, and if you need to catch up on the notes or whatever, then take a few minutes to get your notes complete. Okay, the next thing we're going to talk about is we have another example. And we're going to talk about how sometimes we can actually use a sampling distribution to evaluate a claim. All right, so this example, or this problem, it says to determine how much homework time students will get in class, Mrs. Lynn has a student select a simple random sample of 20 chips from a large bag. The number of red chips in the simple random sample is going to determine the number of minutes in class students get to work on their homework. So Mrs. Lynn claims that there's 200 chips in the big bag, 100 of them are red. When Jenna selected a random sample of 20 chips from the bag, without looking, she got 7 red chips. Does this provide convincing evidence that less than half of the chips in the bag are red? So you might think, well, part A is, what's the evidence that less than half of the chips in the bag are red? Like, why would you even question that? A lot of times when I'm working these problems, we'll answer that question in just a second, I'll go and kind of denote everything. Anytime you see capital N, that's the number in the population. There's 200 total chips. Little n is the number in your sample that you're going to take. And then P, this is the population proportion. How many red are there? 100 out of 200, which is 0.5. So part A says, so a lot of times what I was getting to here is I'll write this information down just because it just kind of sorts things out. What's the evidence that less than half of the chips are red? Well, that has to do with Jenna's sample. So part A, P hat, which is Jenna's sample, was 7 out of 20, which is 0.35. So that might have you question whether or not really there are truly 50% red, or 0.5 if the proportion is 0.5. Jenna's sample proportion is less than 0.5. So that might be your evidence that you're questioning about the number of red chips in the bag. Part B, provide 2 explanations for the evidence described in Part A. Okay, well, number 1, we just talked about something called sampling variability. So maybe this proportion, the sample proportion, is due to sampling variability, because we all know that all our samples are not going to always equal 0.5. It's not going to always equal the true proportion. So that could be one explanation. A second explanation is maybe the teacher's not telling the truth. So those are the 2 possible reasons that, the evidence for Part A. So it's possible Miss Lynn is telling the truth and Jenna got a P hat of less than 0.5 because of sampling variability. Mrs. Lynn could also be lying and less than half the chips are red. So those are the 2 explanations for what happened there in Part A. Okay, so the next part of this question says we use technology to simulate choosing 500 simple random samples. So they did a simulation using technology, and they had 500 samples, size still 20, from a population of 200 chips, 100 red, 100 blue. The dot plot shows P hat, the sample proportion of red chips for each of the 500 samples. So this is similar to like what we did on the problem with the heights, except there's 500 here, okay? And so as we look at this, here is 0.5, and it is in the center. And then obviously you've got some samples on either side that were either below or above 0.5. So part C says there's 1 dot on the graph at 0.8. Explain what this value represents. So here's 0.8 right there. So what that means is I kind of just wrote down in one of the SRSs, in one SRS, in one of the samples of 20 chips, there were 16 red chips. So P hat was 16 out of 20, which is 0.8 for this sample. So that's how we came up with 0.8. It would have to be 16 out of 20 were actually red. Okay? That's a lot of red out of 20. When half are red and half are blue. And there is only one case where that happened. Okay, part D. Would it be surprising to get a sample proportion P hat of 7 out of 20 equals 0.35 or smaller in a simple random sample of size 20 when P is 0.5? Justify your answer. Okay, so the question basically is, would it be surprising to get 0.35 or less? Look at all this data where it was 0.35 or less. I would have to say the answer would be no. It would not be surprising because of how many of these are either 0.35 or less. That's a lot. If you were just talking about that 1 point, that would be surprising. That's not a lot. But when you're talking about all of these points in here, that's a lot. So I said no. There were many samples with P hat being less than or equal to 0.35. So no, it wouldn't be surprising because of that. Part E, based on your previous answer, is there convincing evidence that less than half of these chips in the large bag are red? Explain your reasoning. Okay, so I said that it isn't surprising to get p hat is less than or equal to 0.35 by chance when p equals 0.5. There is not convincing evidence that less than half of the chips in the bag are red. Okay? You can look at this and tell. You've got some samples that were greater than 0.5, like I said. You have samples that were less than 0.5. So it's not surprising, or there is not convincing evidence that there's less than 50%. So what we just did here is we did use a sampling distribution to help evaluate a claim. Okay? All right. The next one is a little diagram that we're going to talk about what all this means here. So what you've got in this first part of the diagram, it's kind of illustrating like this is the population. So there's 100 blue, there's 100 red, there's a total of 100 chips in the population. Okay? The middle part is just two samples. So this sample, there were 8 out of 20 red. This sample, there were 11 out of 20 red. So this is just a sample illustration. This is just two samples. So this was the 500 samples. So this is actually a sampling, or it says approximate sampling distribution. Okay, so when you take all your samples and you illustrate that data, then you have a sampling distribution. So the idea of a sampling distribution is to take many, many samples from the same population, collect the value of the statistic from all the samples, and display the distribution of the statistic. The dot plot shows the approximate sampling distribution of p hat, the sample proportion of red chips. All right, let's fill in the blanks. The population distribution and the distribution of sample data describe individuals. A sampling distribution describes how a statistic varies in many samples from the population. So we just keep hitting on that idea of what a sample distribution is. Many, many, many samples from the population. And it also shows how the statistic varies. It's not always going to equal 0.5. All right, let's talk about how to describe a sampling distribution. How trustworthy is a statistic as an estimate of a parameter? So what they're saying is here, if you find a statistic from samples, how trustworthy is it as the true parameter? So there's a couple things you need to consider: the shape, the center, and the spread when you look at a distribution. A statistic used to estimate a parameter, if you use a statistic to estimate some parameter from the population, it's called an unbiased estimator if the mean of its sampling distribution is equal to the true value of the parameter being estimated. So that's just the definition of an unbiased estimator. I'm going to show you where we had an unbiased estimator. Okay? When we did this first problem on the heights of the brothers, and we found the sample mean, if we went through and we added up all these numbers here and divided by 6, we would get 71.5. Because all of these, if I took all of the sample means and I averaged them, I got the exact mean of the population. That's what's called an unbiased estimator. Okay? This one is not an unbiased estimator. Because if we went through, we can average these up. There's no way that the average of those numbers there is going to equal to 7. Okay? So we'll kind of look at the chips problem first. It says, when you look at the center, 0.5, that is the center of the data. Okay? And notice that the center of the distribution is very close to 0.5, the parameter value. In fact, if we took all the samples of 20 chips from the population, we calculated p hat for each sample, and then we found the mean of all those p hat values, we would get exactly 0.5. And for that reason, p hat is an unbiased estimator. So p hat would be an unbiased estimator because of that. And then this is the one we were just talking about, the brother's heights. So if we went through and we found the mean of the sample range, so these were all the range, and then we averaged them, you get 3.67, and that is not equal to the population range. So since those two are not equal, then this would not be an unbiased estimator. This would not be a good way to, you couldn't really use your sample range for that particular problem because it wasn't accurate. Now you could use your mean because we saw that that was the same. So this was an unbiased estimator and this was not. Okay, spread. Low variability is better. Okay, when you talk about spread, it's the, the variability. So here's the problem here. We're going to talk about this situation. You go and you ask a person or randomly, hey, have you ever watched Survivor on TV? The true parameter, it's 37% or 0.37. That's the true proportion of people who've actually watched Survivor. So let me explain what these two things are. You took 400 samples, simple random samples, and each one was size 100. So each sample had 100 people in it. You can see that that's in the middle, but notice about the variability. Good grief, that's big. There's a lot of variability from the population parameter of 0.37. Now, let's compare that to this one. This one was also 400 simple random samples, but this one, each sample had size 1,000. This had size 100, this had size 1,000. Look at the difference in the variability. Here's the parameter here and here. I kind of marked those so you can see them. The sample sizes of the 1,000 shows less variability. So I think this kind of shows you that the bigger the sample size, the less variability that you're going to have. One important and surprising fact is that the variability of a statistic does not depend very much on the population size. Okay, so it seems to me, or it seems to be true, just by looking at this, that the sample size has more to do with the variability than the population size. There is one thing that we're going to check a lot, starting now, and that is 10 times n, 10 times the number in the sample, should always be less than or equal to the number in the population. So the sample size is really 10%, has to be less than 10% of the population. So that's something that we need to check. Okay. All right. Almost finished. Larger random samples give us more precise estimates than smaller random samples. So the larger number gives us more precise estimates than smaller. Increasing the sample size will decrease the variability, okay, we just talked about, of the sampling distribution. Larger samples provide more precise estimates because larger samples include more information about the population distribution. Variability of a statistic is described by the spread of its sampling distribution. The spread is determined primarily by the size of the random sample. Larger samples give smaller spread. The spread of the sampling distribution does not depend on the size of the population, as long as the population is at least 10 times as large as the sample. Okay? So this is what we're going to check on. All right, so we're going to choose an estimator. Consider both the bias and variability. All right, so bullseye. This is a bullseye. Bullseye is the true value of the population. So the bullseye is the true value of the population, or the parameter. Variability. How scattered are the throws? Okay. Bias. Aim is consistently off in the same direction. Estimate's not accurate. Okay, so what we're supposed to do is we're supposed to match these terms with what's going on here. So the first question is, okay, you wanted to hit the bullseye, correct? And then you want to look at the variability. So how would you, which one has low bias or no bias? This one actually has no bias because it is actually hitting, this is going to match this one. This is no bias. because it is hitting the bullseye, and there's also low variability. Those points are all really hit the target pretty well there. Low, let's see. Okay, so that's no bias and low variability. This one is like that's big bias there. Okay. High bias. Now, do you think that's low variability or high variability? This one would be high bias because it's away from the bullseye, and it's also high variability because look how those are kind of like